Yes,
No, nothing administratively today. Right. So what have we done so far? So far, I've been introducing kind of the basic concepts of usability and accessibility. We have looked at what accessibility really means for web documents, and we started converting simple documents yesterday, effectively, last lecture, so that was yesterday. And just using conversion tools like Pandoc and Make4HD or Tech4HD. And today we're now going to start finally looking at exciting documents, and that's in particular STEM documents. So what I'll be doing today with you is we'll have a quick look into what STEM documents are, what that actually means, what STEM documents mean if they are on the web, what the difference is. And then we can particularly look at what is difficult in STEM, which is not necessarily given in your regular documents that we were converting so far. And then we'll start converting just a couple of simple math documents, and we'll look at, you know, what's the difference when we start converting them directly, and what is the difference when we then actually want to use them and make them accessible in the sense, as we've discussed before, that the structure is there, that things like you know, the reflow of the page works, and so on and so forth. And then in the next lecture, I think, is that on Friday or Saturday? I think the next one is on Friday, if I'm not mistaken. Friday, yes, thank you. So the next one on Friday, then we actually have a good look at how we can make math content directly accessible on the web, and what that means in terms of trying to get semantics, mathematical semantics, into the page and into the mathematical documents, into the mathematical structures.
I think somebody's audio is on. Please mute yourself.
Is that? Yes, good. Thank you. Right. So far we've looked at what the WCAG criteria and the accessibility criteria really meant for just regular, ordinary documents, which could include images and graphics, but we didn't really dwell too much on that. So we saw, for instance, the images of the cats, which were hiding some links, and there was no alt text, and so on and so forth. Today we're going to start looking at what this really then means in a context of complex scientific documents, i.e. STEM. STEM, as usual, stands for science, technology, engineering, and particular mathematics. Because one problem that we have with these documents is that the WCAG criteria, as we have learned them so far, in particular A and AA, do not really apply at all. That means they're generally satisfied, but the document itself is still pretty much inaccessible, because STEM documents are rarely accessible out of the box. And even if WCAG is satisfied, even if all the criteria tick the green boxes on our evaluators, the readers that have special needs often do not really get the content that they're expected to get. And why is that? Well, the easy answer is, of course, because STEM is hard. We all know science is hard, math in particular, or it's claimed to be hard. I always claim it really isn't, but that's not everybody's thought. And what is the long answer? Well, the long answer is, well, it actually depends on what you do with your document, but it still relies on the fact that STEM is hard. Even if you know what you're doing, you have to really be careful in order to get the document onto the web in order to make it fully accessible. And why is STEM difficult? What's the concepts in there that really are difficult in order to make documents not only accessible but usable, and so on? Well, there's a bunch of problems which is generally considered the hardest of all the accessibility problems in general, and they all come together in scientific documents. Some of them are just having to do with ordinary elements which occur as such in normal documents as well. So, for instance, there's a vernacular. There's vernacular in normal documents, but in most documents it is particular language, or particular language, say it's a poetic language or it's a language about history or something. But in STEM, it's generally a very highly specialized vernacular, which is only really well known to some people, meaning that you can't just go to and look it up somewhere in a dictionary. You can't get help in that way. Instead, you really have to know what you're talking about, and such as you have to also make it accessible in the way that you know what you're talking about. There's different scripts involved. I'll show you a couple of examples later. There's tables. Generally, there's tables in normal text as well. However, in scientific text, they're generally a lot more complex and involved. There's, of course, when you talk about mathematical content or physics or chemistry, you normally have formulas. You don't just have formulas, you have diagrams, and these diagrams are not just there for illustration or for demonstrating a couple of things, but they are really there in order to convey content, and important content. And sometimes they are the only things that convey that content. And that's just the traditional content. In addition, you can have nowadays on the web, you can have all kinds of other things. You can have animations, three-dimensional graphics, three-dimensional models that you can rotate and that you can spin around and look at it from all angles. You can have, of course, videos embedded in the page, or the video is the main thing. Think about COVID-19. The video these days, i.e. me talking to you from Birmingham in the UK, rather standing in front of you in the classroom, is now the main means of teaching. So that is an important aspect. Other things are dynamic content, so things that can change by input, by user input, as well as by user expertise. You can have simulations and all kinds of other things. And we'll look at a few of these things and the accessibility problems in just a few slides. Right, so let's have a first thing about what's particular about scripts and vernacular. What does that even mean? Well, scripts generally means that you have different scripts from different alphabets. Well, on the Indian subcontinent, you're very well aware of these things. In Europe, it's not necessarily the case, but what often happens in scientific documents is that you mix, for instance, Latin characters with Greek characters, as well as with special symbols from special character sets. And let me give you, and that generally throws assistive technology devices off. And let me give you a screen reader example, and I'll go to a different browser for that. And let me switch on a screen reader as we've done yesterday. Let me switch on my Chromebox. There it is.
Alert. Document accessibility tab. Generic container.
Can you hear that?
Window tab. Alert.
Yeah, we can hear.
Okay, good.
Wikipedia tab.
So this is about DNA replication, and it's not necessarily very complex. It's not necessarily very complex vernacular, as in the scripts are, there's a bit of Greek in there, as you can see. There's a gap, there's a phi, and I think there's alphas and betas. That's normally how you express proteins, but if we just start reading one of these paragraphs, let's go to this one here. Let me make it a bit larger for you, and let's just read that out.
DNA polymerase has 5-3 activity. All known DNA replication systems require a free 3' hydroxyl group before synthesis can be initiated. Note the DNA template is read in 3' to 5' direction, whereas a new strand is...
So just, you probably have heard that already now. What is the problem? Well, first of all, it doesn't speak everything that's necessary and that's important and that's there on the page. So if, for instance, it said has 5 to 3 activity. Well, that's not enough, right? There's a 5' and 3', and the prime is important. The screen reader later then actually tries to speak it, but instead of speaking it, and let's just speak it again.
DNA polymerase has 5-3 activity. All known DNA replication systems require a free 3' hydroxyl.
Right, instead of saying 3' hydroxyl group, which is a specification telling you exactly where the hydrogen is on or where the oxygen is in that particular group. It says 3 feet because the screen reader is very smart and things like, yeah, every little dash behind a number must be feet or inches, right? Which in that case is entirely irrelevant, entirely wrong. And that's just one of these examples, and that's a fairly trivial example. You can imagine the more involved a text becomes, the more problematic these things are. So there's omissions, there's mispronunciations, there's all kinds of issues that you might end up with if you're using a screen reader naively on text that has to do with scientific content. Right, and it's always important to know is that there's no such thing as just learning how a screen reader will pronounce it. So for instance, you could say, oh, well, we just have to now start learning that in this content, when they say 3 feet, it actually means 3 prime. That's generally not enough because, first of all, not every screen reader reads in the same way. And the second, and that's much more difficult, the problem is that these voices are retrained on a regular basis. And if, depending on what they're retrained on, they might change how they pronounce special symbols. Right. So, for instance, there's a classic example. Some of you might be familiar with Waze. Waze is a navigation tool, and which was recently acquired by Google, and it gives you directions. So it gives you directions, but it also has a social media component, so you can automatically get update on whether there's a traffic jam somewhere, etc. Because people in front of you in the queue might broadcast that. And the Waze voice for some time had a problem that instead of giving directions, it would say things like greater than and less than, because there was a little arrow to the right or a little arrow to the left, meaning that you have to exit, for instance, on a motorway. But instead of saying, well, exit 3, it would say greater than Cambridge, meaning that you now have to exit to Cambridge, which obviously is a problem with a voice being trained on a mathematical data set rather than on a data set that is good for navigation. Right. And that is another problem, is that you can't really train these voices as well as as other assistive technology tools, which might provide you with transcriptions, for instance, on a particular set, which then will stay constant, because that's the whole point about scientific languages. They are in principle infinite languages. That means that not only does the vernacular shift and is being extended on a daily basis, but it also means that it's aimed at various audiences. So I can change the language depending on whether I want to talk to pupils in primary education, whether I want to talk to students, or whether I want to talk among scientists who really know everything about the language they're using. And as a consequence, you can't really build dictionaries for these languages. You can't really have a declarative approach, and therefore things like automatic voice recognition often fails, which is currently very important when we talk about subtitling videos, particularly videos of lectures. And it is also important that you cannot just have a vague understanding of the language, because precision is very important. So you can't just go ahead and say, well, there might be a molecule in that image. This is all I can recognize. It's enough for a Facebook picture, for instance, to say, oh, well, there might be 3 cats in there. And that's great. That's great for Facebook image recognition. But if you do the same in terms of image recognition on a scientific document, then it's not enough. You can't just say, oh, well, there's a molecule. We don't really know what molecule it is. Could be, could be aspirin, could be paracetamol. That's great. Could be heroin. Then it might be deadly if you give it to somebody. So in that case, it's not an easy task, and that's why STEM is a hard problem. Tables. We're still going through examples. So tables is is difficult as well, because tables are not necessarily standardized as you know them from regular tabular formats. So here's a table about DNA code. You might wonder where the table is. Well, there's a bunch of tables on that page. If you can see the page, there's a couple of nicely colored in tables. But what really is the interesting table here is the cordon table on the right hand side up here. And I'll bring it up for you. So this is a table which is not really a table. This is more a disc shape. So you start inward out with 4 cells on the inside, and then you have 8 cells on the outside. No, it's not actually 8 cells. It's 4 times 4, so it's 16 cells, sorry. And then you have 4 times 4 times 4 cells in the next ring, and so on and so forth. And all this gives you then an overview of the combinations of amino acids, I suppose, that make up the ribonucleic acid, the RNA. Right, so that's one particular table. Other tables are, for instance, when you have when you look at the families of animals and species, etc., which tend to be not really like tables, more like mind maps. What else is important about tables? Well, so often you have various. It's often more important to actually look at the shape of things in a table. So here are the bell numbers, for instance. And as you can see, for the bell numbers, what's not that important are the actual entries. What is important is that you can get a feeling for the growth of the numbers. And the growth of these numbers is, of course, exponential. So you can get a visual feeling for the digits. The number of digits are growing. So what you rather see here than the actual digits, which is what a screen reader would read out for you, is you want to get a feeling for that curve that is being described by these digits. So for those of you who can't see the slide, is that the bell numbers for 1, 2, 3, 4, 5 up to 9 they grow exponentially in the number of digits that they generate. So for instance, the first ones are single digit long, then 2 digits, then 3 digits, 4, 5, and so on, meaning that you get these the curve in terms of the size of the digits. And other things that are often more important in scientific tables are, for instance, empty spaces. Right. So here are the Euler numbers or number series, and obviously here's quite important to see where the spaces are empty rather than where the spaces are filled. And that's a common phenomenon which you also get for matrices, sparsely filled matrices, and so on and so forth. So simply reading these things out is not necessarily something that is particularly helpful for people. What else is there? Well, formulas, of course. Formulas is a hard problem. Why is it hard? Well, it's for generating audio, it's difficult because it's always difficult to understand what is the exact reading order of a formula. If you recall what we did in the last lecture, where we were talking about particular regions in a document, which gives us the reading order in which we want to read it. The document is being read out, for instance. Subsections follow sections and so on. That is difficult to see in a formula. You have to understand what the formula is about. You can't just go through it from the left to the right because it's a two-dimensional thing. Consequently, other elements are difficult. Zooming, what is the important part we want to zoom in a formula? If you want to do highlighting in order to support people with dyslexia and dyscalculia, for instance, then it's important. What are you highlighting? What are the things that you actually want to set off against each other? If there's too many symbols in there, you might have to alleviate that symbol clutter. How do we simplify that? How do we collapse certain parts, things that should be at a first view or at first glance should be hidden before somebody can no longer see what that formula is about. And obviously, again, for videos, for instance, voice recognition for formulas is extremely difficult. How do you do subtitles automatically when you lecture on mathematics? Just a couple of examples of formulas. Here's a big one. Oops, that's from the Digital Library of Mathematical Functions. And as you can see, if you can see it, I can't really read it out because, to be quite honest, this is already hard for me to read out. But it starts with an open brace here, and then there's effectively it looks a bit like a 2D matrix, and not 2D matrix, or two row matrix. But it really isn't, because what's important is that J1 goes to L1, J2 goes to L2. Though you've got two rows, but effectively you need, what's interesting are the column components, and then afterwards you have an entire clutter of symbols, which some of them are distinct, divided by a division line. Some of them aren't, because they effectively are representing, again, a mapping of that nature. And so this is, for instance, a formula which is very, very difficult to read out or to get across to somebody who can't see it. Even people who can see it might have a hard time understanding what the hell is going on in there. Other problems, and that is a little problem which has to do with the layout. If people do their own layout for particular pages, formulas might be broken up. That's something that's not easy to see if you just look at it, because it visually looks fine. But if I just click on that formula, you can see a rectangle showing up around it, and that indicates that the formula is actually being broken up at the equality sign. And if I now were to read this out, now I don't have a screen reader on, but I'll show you with a subtitle element here. I'm not sure whether accessibility is switched on. Let me just do that. This is something I'll explain to you later, how that really works. We'll do that in the next lecture. In this lecture, you can see, for instance, that now if this formula would be read out, it's only the left-hand side of the formula that would be read out, and it's not clear for somebody who can't see the visual connection that these two formulas are actually connected to each other. And that's a common phenomenon on these pages in the Digital Library of Mathematical Functions. I know the guy who's doing that, and he's doing a great job, but obviously a lot of it is geared towards visual layout, which is already hard, as you can see here on these big pages, or these big formulas on the page, and therefore it's not always well done. Well, and obviously then you can have all kinds of badly formatted formulas. Let's wait a bit until this thing renders, where things are kind of crossing the lines, crossing the vertical line baselines, and where it's unclear how they're actually fitting together, even if you're seeing these and can actually see and experience that. It might be even easier if you can listen to it. Actually, I'm not quite sure what this thing would give. It's massive. Other things where you have for particular constraints, for instance, those are then broken off. It's not clear anymore where they belong to, and so these are all kinds of small problems in many ways, but problems that accumulate and add up. Right, and that's only the standard material, right? What about graphics? Graphical material, again, what our WCAG guidelines say is that all text is satisfactory. So if you have a graphics element in the page, all you want is an alternative text description. That is not generally enough. So here's an example from biosynthesis, somewhere down here probably. Now this is a massive graphic, and that graphic in many ways contains the entire content. Now, trying to just put alternative text in it for it, in the Wikipedia entry here, the alternative text is, and you might be able to see that when I hover over it, it should show up. Oops. Well, yeah, there it is. It just says phosphatic. I can't even read that. What phosphatidic acid synthesis. I don't know, that's 5 elements in that page that all come across, and that should be read out. Unfortunately, you get a 3-letter abbreviation. All the rest or interesting part is hidden in the image. And if you actually read on that page, then what it's not really a caption here, but what's underneath the diagram actually explains what the diagram is about, so that there's a pathway and it starts with one element, which is a glycerol 3-phosphate and so on, and then how it carries on. It doesn't really explain all the arrows in the image, and it doesn't explain all the dashes between the atoms, but at least it gives you some idea. If you go further down, it's unfortunately no longer the case. The image, it just says at some point, well, this image denotes that, and that's it, right? And the image is even more massive. It has 5 components and a lot of arrows between, and the old text is just 2 words, which is phingosine synthesis. As I said, I can't even pronounce that. Neither can screen readers, by the way. And there's even worse on that page. Right? Right, so clearly I've got even more nicer examples for you. This is, I'm afraid, it's a fairly graphic-based start of the lecture. So if you can't see the slides, I'll try to explain as much as possible. But so again, we're talking first about 3D material from the Digital Library of Mathematical Functions, for instance. That's 2-dimensional methods of functions, of course, but here 3-dimensional is even slightly more exciting. So you can actually bring this up and you can play with it, and that I suppose this is a complex function which is being displayed here in a heat map, and so you get the maxima and the minima nicely, and you can spin the whole thing around, and you can have a look at the minima where they lie, and so on and so forth, and the valleys, and you get all these things, which is great to look at, great to play with if you have the possibility to see it, and if you can discern the colors. Let me just, for the fun of it, let's just switch this into what happens if we switch this into a different contrast mode. There you go. You can still see the different colors. Now let's go to yellow on black. Obviously now all the colors are gone, and inverted grayscale. It's then all of a sudden all the fun takes a bit of the fun out of it. But in many ways, you can still see roughly what's intended. It's not as nice anymore. But this is obviously something which is difficult to get across to anyone who can't see the graphic at all. It will be difficult to describe in speech, and it's practically impossible to emboss. We could think about maybe a 3-dimensional printing model, but that's about it. Other things, dynamic calculations. So this here's calculator soup, for instance, where you get dynamic calculations. Where do we have one? Maybe statistics. Let's get to see. You enter something, and let's try to do something like this, and then all of a sudden things are happening on the page, and things are changing dynamically, and the formula being adapted to the dynamic version of the data that you've entered. You can get that even better. Phil Stark's sticky GUI, for instance, is a very nice example where you can enter all kinds of things into your statistical data visualizations. And let's just, it's not nice. Let's go for this. You can add lines, and you can change the data, and things are happening on the screen, and it's all very nice and interactive graphics. And unfortunately, there is no accessibility in this particular example provided. That all of this, in many ways, is only possible if you have the full range of accessing the page visually, as well as with your point-and-click device. Otherwise, you have no means of using that. I'm mindful of the time, but I'll still show you the fit simulations, because that's something we're going to look at some point in slightly more details, because they're making a good effort to making things accessible, at least for some of their simulations. And I'll show you what these simulations are about. So it's an interactive simulation environment in which you can start. Let's just have a look at the solutions in which you can put together easily simulations for your class when teaching, and then these simulations have a couple of activators like slider bars where you can slide things up and down, and then here you add in there you kind of, it's supposed to be some sort of a solution, I suppose, which contains a number of elements and the molecules. And you've got a formula below it, and you've got a view into the solution, and where you can add more molecules or you can remove some molecules, and then you can look at various graphs, how they resolve, and you can do all kinds of fun things. I believe you can change the pH value. Is that somewhere? Yes. I'm not quite sure what that really does. So if you know what you're doing, you can probably you can reset it. You can probably learn something with it. But the idea is, you give that to your students. They can play with it. They can use their own parameters, and then see what happens. As I said, those FET simulations are actually quite accessible. So they have accessibility solutions in the background. And we're going to look at those once we start talking about how to get semantic into our documents, probably next week. Right, so for now, we're going to be content just to look at math documents. And we'll start with fairly simple math documents. We don't really care too much about diagrams yet. We think about what formulas are and what the formulas in the documents are, and how we can make them web documents, and how the formulas can then be rendered on the web. And also we're going to discuss a bit about other things that happen, particularly in math documents, like equation referencing, specialist environments like theorem environments and so on, cross-referencing and so on and so forth. Right. So let's have a first idea of what can we actually do with math. Well, math has been moved to the web since the very early beginning, obviously. I mean, some of the motivation behind designing the web was communicating about scientific data. I mean, originally at the same time when the World Wide Web was invented at CERN, there used to be a different method how to distribute data amongst scientists, and that was called Gopher. So there was always FTP, where you could just put things up, but you couldn't really find anything. But then there was something called Gopher, which was a protocol which very similar to the hypertext transfer protocol, where you could do searches, etc. But it was primarily data-based as well as text-based, meaning that you couldn't really display anything. So that was quite easy. The formulas at the time were just, they were there as LaTeX. Tech was available. Everybody knew it pretty much in the community, and therefore formulas were just LaTeX, and you would just kind of pull them down and look at them after rendering on your local client. Once the World Wide Web kind of started taking over, people started putting mathematics on their websites, and there was all kinds of ways how to do this. And obviously, the easiest was always, and that's a really old one, I'll show this to you here, is what, for instance, happens in Wolfram's Math World is putting it there as an image. And you can see here's the quadratic formula as images, and I can track that out, and it's a simple bitmap image. And if you look at that, the larger I go and the more I zoom into it, the uglier it gets, and the less you can see. You can see all those checkies coming up, so jagged lines, and it's just, the rendering is just atrocious. an alternative which existed from fairly early beginning of the web was that you could render at least certain things as HTML elements, because you could set things up in various ways. And here's an example where people still do that. That is just pure HTML in there. You can you can highlight it, you can copy it and do everything, but in many ways, all it does is using the HTML ways of setting things above and below the baseline, and therefore you get fairly ugly. Let's face it, fairly ugly formulas. And so, for instance, here the radix and the top line of the square root don't even work together, and it's just. And it's also not really accessible. What else? More modern versions then is rendering it in a modern diagrammatic version is, for instance, rendering it as SVG, as scalable vector graphics. Here's a version how it's rendered as scalable vector graphics in the Wikipedia. Now these quadratic formulas here, if you can see, they're still images. I can pull them out, I can drag them around. But they scale nicely because what they are actually scalable vector graphics. I can just look at the image itself, for instance, in a separate tab, which certainly doesn't work at the moment apparently. But this is an SVG. I can zoom it as much as I like, and I can potentially put information in it as well if I want to. Oops! Oh, there it is. And finally, you want to have it maybe natively rendered in the browser, and that's what certain libraries do. This library is particular MathJax, which I'm involved with, and what that does now is it gives you various ways of displaying it. For instance, here I'll have also a way of displaying it as speech, which could be spoken out, and this is indeed the speech I've set up here. So apparently that's German. So you can read it in various languages, and so it's fully scalable as well. And oops. And so in many ways, the last two examples were the examples that you really want your mathematics to be in when you have it on the web, and that's exactly what we're going to start after the break. That we start converting the first math documents with the tools that we started learning last lecture, which was Pandoc and Tech4HT. And we have a look at how well these tools perform, how the math is being rendered, what can be done with the mathematics once it's in sight, and how can we render it well. And then we also have a look at what are we going to do about things like structure, layout, and reflow, and how that can be done with these systems. So so we'll get documents that are fully usable on the web, and then they will give us the basis to start making everything nice and accessible in the lecture on Friday. So let's take a little break, about 5 minutes, and then we'll start with converting mathematical documents, primarily LaTeX, but we also have a Word document. If you haven't installed Pandoc or Tech4HT yet, by all means, if you want to play along and if you want to share your screen, then you should do that during the break now.
Thank you. So we will have a 5 minutes break. Before you break, I just wanted to make one announcement. So I see that only very few people have registered for, preparing the manuscript from the lecture. So I would encourage many more to do that. We will keep it open for another couple of days. Please understand that this will help you also to not only understand this and also to sort of contribute to a larger cause. Okay, so please do volunteer, and we will, if we have enough people volunteering, we will have a very good document coming out of it. Thank you.